Hello everyone here from Germany. My name is Philipp Abel. I work as a product manager for Spectrum Monitoring Solution at LS Telcom, and I want to welcome to you today to my presentation, Next Generation Spectrum Monitoring, the Role of AI and Big Data. LS Telcom is a worldwide leading company in spectrum management solutions, radio network planning, and what is the topic of today, spectrum monitoring. And we have recently founded a dedicated team who will focus on the topics artificial intelligence and big data, and we bring step-by-step innovations of this field into our product portfolio. And some of you, really nice innovations I will present to you today. So I will talk about next generation spectrum monitoring. Why do we need a next generation of it? We can see in the last decades, in the last 2 decades, the following spectrum usage trends. So we have new emerging technologies like UMTS, LTE, the newest technology, 5G, Wi-Fi, Internet of Things. And what we see in general is an increased spectrum usage in higher frequencies. We have smaller cells, less coverage, low-powered emitters, and more spectrum users, so the uplink monitoring becomes relevant. And all this really changes the requirements for monitoring systems. So from a traditional monitoring system, like you can see here, this really heavy infrastructure-based design, only a few stations per country, which mainly look at lower frequency. We have a shift towards modern monitoring system. Here you can see a product of LS Telcom, the LS Observer Spectrum Monitoring System. We have multiple smart sensors for various applications, like for fixed applications, mobile based on a vehicle, or portable, or even you can see here we have a flying LS Observer, the airborne monitoring, so monitoring based on a drone system. Those sensors, in contrast to this traditional station, can be really easily installed all over an urban area, like on lantern poles, on rooftops. You can put those devices inside a vehicle, so a really flexible and modern system. Everything can be centralized control. That's a status quo with our innovative LS Observer system. Now you can see here another arrow. What is the future of this? The future we see, and we also have experience with it, is public transport-based monitoring. You can see here some example of it. So using public transport like buses or service vehicles, garbage trucks, or taxis to perform monitoring. Equip those transports with monitoring equipment, and you will have an extremely dense data set. What are the advantages of this? So those vehicles drive around the entire city area all the day. So you don't need to have a specific monitoring team with vehicles who drive only for monitoring through the city area. You can use the platform of public transport like buses. They drive all around the city area day by day. And if you equip them with monitoring equipment, we have their special solution with our LS Observer. You can really collect an enormous amount of spectrum data for the entire relevant frequency range day by day. For example, you can capture with our LS Observer, we have different products from 9 kilohertz up to 6 gigahertz, or even up to 18 gigahertz of spectrum with one device. And yeah, this, like I already introduced, this amount and density of data cannot be achieved with fixed stations. If you want to use fixed station for this, you would need, in an urban area, you would need thousands of stations or even more. So better use public transport as the platform. And we have, as I already said, we have experience with this approach. And one example, to give you an example, what does it mean in terms of data amount? For 8 hours driving through the city area, our LS Observer collects 300 gigabytes of data if we have a frequency range from 85 megahertz up to 5.38 gigahertz. A really enormous amount of data. And so there's a special hardware needed for this. And here you can see two products of our portfolio, the PPU, Protected Portable Unit, and the Smart Monitoring Unit, SMU. And those units can 24/7 fully autonomous capture spectrum data. They include a large internal storage, so everything is stored locally. They have power management, UPS, so they can either used in a dedicated monitoring vehicle or really in public transport where nobody touches it. So they can really operate standalone. You can also have remote access to this. They can remotely control, for example, via cellular link using LTE, using the public LTE and a secured VPN connection. And all the captured data day by day can then be uploaded, for example, if the bus goes to the bus park overnight via a Wi-Fi link or cellular link or cable, multiple options possible, and all this data can then be uploaded to the central server. Now you have a lot of data. You can see only one drive, 300 gigabytes. What to use, how to use this data, how to make use out of it, out of such a mountain of data. And yeah, this is really big data. We can call this this application, and you see such a massive amount of data cannot be read and analyzed by human beings. So it's too much of data. So the pure data itself is really useless if you cannot be analyzed. So what's the challenge here? How can we visualize this amount of data? If you look at the typical power versus frequency and link waterfall chart of spectrum monitoring, it's not useful in this situation. You have chart by chart, and you need a lot of time to analyze this. This brings you nothing. So you need an aggregated picture for this. Also in the spectrum monitoring world, you may know this classical drive test visualizations. That means the software makes points along the route where you have driven, and these points are color coded though. That means in a point with a more warmer color, you have a higher field strength. That's a typical visualization. But for this, it's also a limitation. You have also you don't have a continuous picture. You only have the points for the area where you've driven. Yeah, and you better need a continuous picture. And the answer we have as LS Telcom with our software solution Spectrum Map. And what is Spectrum Map? Spectrum Map provides a continuous field strength map based on aggregated interpolated monitoring data. Like you can see here on this map, so a heat map, a field strength map. So red means there's higher field strengths, going to the colors more into the blue means lower field strengths. And this is no simulation. Yeah, you might have seen this from radio network planning tools. We also offer this as LS Telcom theoretical calculations. But here you can see it's really based out of a big data from monitoring. It's real data collected from the drives, either with monitoring vehicles or using the big potential of public transport. And it's a really meaningful and easy to understand visualization format of this big data. You can evaluate the real world spectrum usage and the real world service coverage. In this tool, we have various visualization options. I will come to this later. And this provides a really great decision basis for spectrum managers. Yeah? They have a a good, easy to understand picture, and then can base their decision on it, like assign new spectrum at a certain region to identify overloads, to identify white spaces. And there are multiple applications possible. And here's a short video how this works. It's a browser-based software. It's a server client software. So the data processing works on a server and the client is in a browser. You can access this with a standard browser. And now define the area where you want to do your analysis and define which service you want to analyze, and then it calculates you a heat map. This is from a reference project we had in Shanghai, where it's also based on mobile units, which did a lot of drive tests. And you can see you can adapt the heat map, the color scaling, everything. What else is possible besides a field strength map? For example, a coverage analysis, like you can see here. You can define a threshold, what is covered, what is not covered, and you can see only red and blue. And here you can see the whole thing is also dynamic. Yeah, we have a dynamic slider where it automatically slides through the channels of a dedicated band. So you can define all the channels and you can have this slider view, really dynamic. You can see how the spectrum picture, the heat map changes channel by channel. Multiple applications possible. This was only a short introduction of this. If you want a dedicated presentation, just contact LS Telcom and I will provide you a detailed presentation of Spectrum Map. How does now Spectrum Map do the whole thing? So we have at first the data collection from various units. Could be a mobile unit, so public transport or dedicated vehicle. Could be also from fixed stations with various different sensors. Do not need to be LS Observer sensors, can also be sensors which are already in use from other manufacturers. All those collected data can be combined together. That's a data mining, data fusion, and on the server, and then everything for the user is then rendered. You have multiple visualization options like heat map display, you saw dynamic display. You can compare different points in time. You can compare the spectrum situation of different days, how it changes. And you can also compare different frequency, different bands together. Yeah, another reference project we did recently in Dubai. What we used here is a really simple setup. So we just use an existing vehicle there, a standard SUV vehicle. We brought just with a plane our small antenna with it, put our PPU, this box you saw before, inside of the vehicle, and drove around 3 days over the entire city area. And after each day, when the vehicle comes into the garage, all the data was automatically transferred via Wi-Fi. So as soon as our unit picked up the Wi-Fi, all the data was transferred to the server and then automatically processed by Spectrum Map to provide such a heat map. And we did achieve really great results. I can show you in the next slides. And the regulator there also plans in future, they have this concept in mind, also plans this doing based on public transport. At first phase on existing vehicles with dedicated drivers, but they also plan it on public transport. So really innovative design here in such an innovative city like Dubai. Really nice to be part of this. And in addition, we have there the LS Observer CMS software, so the central management software of our LS Observer. With this, you can then do deeper spectrum analysis, like if you have some interference, you can evaluate it, you can measure bandwidth, you can do demodulation, you can do geolocation. This is done with LS Observer. And we achieve really great results, really nice spectrum map. it's confidential now to tell you which frequency it is, but you can see a bit how the maps will look like. So you have for each frequency you have certain hotspots. Especially if you look at the uplink, you can see where the highest frequency usage is. On the other side, on the downlink, you can see where do I have coverage, where do I have white spaces, and yeah, we really achieved great results. And Spectrum Map really we did with the 3 days. We merged all the days together, and yeah, it provides such a nice and easy to understand picture. It was really impressive. And what use cases can you expect with Spectrum Map? Only I've listed a few of them here. So for example, which I already mentioned is coverage. You can, for example, look at the cellular coverage, see the aggregated view of the whole 5G band, for example. So where is 5G in general available? And then you can look also to the individual providers, who provides the best coverage in which area. Are there any white spaces? So you can see where 5G is actually in use. Or look at the uplink, yeah, look at where the users are, where you have a really low or high dense usage. You can see it by looking at the uplink, and there it's important, as it's really low powered there, it's important that you on the streets that you're directly next to the users. Yeah, from a fixed station anywhere outside on top of the mast, you cannot pick it up. So this concept on public transport is really the solution for this use case. And also new technologies are interesting, like narrowband IoT, where it's available, where's by looking at the downlink, yeah, but where it is actually used, yeah. Is it used, for example, or is it available in industrial or smart city areas where it's really needed, and what is the coverage of it? Also looking at Tetra, which channels are used? Do you have overloads? Looking at Wi-Fi, doing the same. Do you have overloads? You can compare, as I already said, different days with the time slider. How does my spectrum of my entire city changes over a week? Also, what is interesting use case, you can load up a database of your existing stations to Spectrum Map, and then you can display the stations on the map, and then you can see if there is any hotspot where no station is, no licensed station. It may be an illegal station. And that's really interesting. From this big amount of data, you can even locate illegal station without needing any geolocation technologies like direction finding or time difference of arrival, only by analyzing this big data set. And so what is the general use of Spectrum Map? So Spectrum Map can be used in spectrum management process. It can be used to compare really the theoretical calculation with a real world picture at the assignment process. So you get a picture where you can base your decision on it. Is the real world picture different? Is the spectrum clean for the assignment? Or can I assign spectrum only to a limited area? You can identify spectrum usage for a assigned service. Is this really used, or can you reallocate it to a different service? You can identify overloads. Do I need, for example, to allocate more spectrum to individual service? And what's also an application of Spectrum Map is that you can map the electromagnetic environment to verify it against compliance to national rules. So you can prove it to the public that there's no hazard from electromagnetic radiation. You can give them an official map of this provided by Spectrum Map, and they can use in which areas there's more radiation, in which areas there's less radiation, and if the thresholds are met. Okay, yeah, this to the great spectrum mapping functionality which we provide at LS Telcom. Now, as my topic is also my major topic, artificial intelligence, how can AI be used in spectrum monitoring? And for this, we currently are doing developments in 4 different segments for monitoring. It's one thing is AI for anomaly detection, like interference. Then we use AI to increase the infield accuracy of direction finding. We use it in signal classification and in frequency assignment. So first, to start with anomaly detection. So the AI needs to identify there the relevant data, the anomalies within the huge mountain of captured spectrum data. So you can see mostly you capture a lot of data, but only a minor part is relevant. And this to do by human analysis is, depending on the amount of data, it's not possible. So best to use here artificial intelligence to really identify this small portion of data. And what is relevant data here? For sure, you want to know about interference, you want to know about illegal transmitter, you want to know as a regulator if license conditions are violated, or you want to know if there are any transmitter failures or any capacity overloads. And all this needs to be identified automatically by the artificial intelligence. How is this achieved? The topic is here machine learning. So first target is to train the machine to differentiate between the normal spectrum situation and any anomalies like you can see in the list here. Yeah. Now the problem is what is an anomaly is depends really on the use case, the definition of it, and its harmfulness. Yeah, for some customer, for example, a small noise caused by LED lighting system at the Tetra range is not so important because the system is robust, or they do it they need Tetra only for not critical things. For another customer, it's more relevant. So what is needed here is that we have an initial phase where we put our monitoring system on site, and it's a supervised stage where it learns the situations on site. So someone needs to tell the system what is really harmful, what is not, and then the system learns step by step automatically to do this on daily operation in an automated mode. Yeah. So second target is also to train the machine not only to differentiate between normal and anomaly, also to classify the event. What is it? Is it interference? Is it emitter outage? And to evaluate their relevance, yeah, to not give false alarms. If an interference is not really relevant, then no need to give an alarm. And then what is now to do if you have an alarm, if you're alarmed from interference? The AI should give a recommendation how to solve this problem, this individual problem. Yeah, and this AI-based AVD we will implement. We will work on this currently. We will implement this at 2022, 2023. And we will base this on our current implementation. It's called AVD, Automatic Violation Detection. It's already used for really to detect different scenarios. You can see how it works here. I have a small video. You can build up mask as a user over spectrum. This is, for example, GPS L1 band. And as soon as someone happened, here, for example, a jammer is active, you will get an alarm. So in this case, there's a red flash, and you can connect it to an email server, and then you will be informed by email as soon as an alarm happened. And this can not only do for one channel, but for all your channels, all your bands of interest. You can define those masks based on a reference level, an upper and lower threshold. And if then the signal goes above the threshold, you will be alarmed. And this will be in future get even more sophisticated with artificial intelligence. Then the next topic is direction finding accuracy. First, what is direction finding? It's typical application in spectrum monitoring. You need a direction finding antenna, either based on a vehicle, like in this use case, or based on a fixed station. This is actually our product, our AOA1XX antenna. It's a unique product as it can also perform direction finding not only live as usual, but also based on stored spectrum. And the stored spectrum can be like from 9 kilohertz up to 6 gigahertz, up to even 18 gigahertz. And you can pick up any signal in the stored spectrum and can perform direction finding subsequently in your office, for example, after a drive test. And what are the results of this? So if you do direction finding, you get a line of bearing. Here you can see one, then go to another location, make a next line of bearing, and you have a triangulation, and you can locate the signal source, like displayed here. You can also add, this is in our LS Observer CMS software, a screenshot, also supported by heat maps to get the user a better view where the search signal is. Now, what about accuracy in direction finding? So typically, direction finding antennas have a value, it's called degree RMS value. Yeah, this is the accuracy, like for example 2 degrees RMS, but this is defined based on an open field environment. Yeah? There's an ITU recommendation that how to measure it. You measure it in open field environment, in a laboratory environment, which has nothing to do with the reality. Yeah? To be able to compare different values from different manufacturers. But what about the infield accuracy? And here's a problem. Here you cannot have an accuracy value because it varies so much in the field. If you're not in this laboratory situation, if you're in the field in an urban area, you have everywhere neighborhood imperfections. You have metal structure, grid towers, buildings, and so on, which will reduce your direction finding accuracy. And yeah, this topic we want to capture with artificial intelligence. We want to have, by adding AI to this, an outstanding infield accuracy. We want to resolve this these accuracy errors by using a permanent calibration, AI-based calibration. What does this mean? Typically, an DF antenna is calibrated first in the factory, yeah? And then is used in the field without any calibration again. And this initial calibration will then replaced by us by an initial factory AI training, so machine learning. This will at first day already improve the accuracy in comparison to a traditional calibration. And then what's now the interesting thing is that we permanent calibrate the antenna in the field by using reference emitters. With CMS, with our LS Observer system, you can connect your database of a licensed transmitter. So you can upload your licensed transmitter. So these LS Observer system knows about all the stations which are in the region. And exactly those stations, as it knows the location, it uses for the calibration. So if you imagine this situation here, you have some direction error caused by a neighborhood imperfection like reflections. Even the vehicle itself can have an influence on the direction finding accuracy. And this error is identified by our AI calibrator because we see, okay, this reference station, which is here, should be here, because the direction finding gives you a different result. Yeah, it gives you a result. It's actually, for example, 2 degrees apart from the actual situation. And as we know, the real situation of the reference, the real location of the reference stations, we can estimate the direction finding error. And for sure, we do this not only for one station, we have multiple stations, and it's best if you have multiple neighborhood stations. And also now it's getting complex is which stations can you use for the calibration, which stations do provide enough signal to noise ratio, for example, to have a good calibration. And for this, we use our internal wave propagation calculations to pick up the stations, the perfect stations for this calibration. As we're also an expert in wave propagation calculation, we use here our know-how. And this is done permanently in the field, this calibration. And with this, you will then achieve a really outstanding direction finding accuracy. That's a really new technology on the market, and this will improve direction finding in the field massively. Yeah, this to the direction finding. Then we also plan to use for the next 2 years, we plan to introduce AI-based signal classification. So what is here the advantage of using AI? The advantage is that the AI can again adapt to the on-site situation. Yeah, if it's on site, a different situation, if there's a bad reception quality or if there are new signals, the AI can learn this situation and can then make, in comparison to commercial product, has a bigger operational hit rate. And with this, we plan to, at the first stage, that the observer can identify more than 20 different modulation schemes, and this information about which modulation is used can then be added to other parameters which we save in our database, like the frequency, the bandwidth, and so on. Then, last but not least, the AI-based frequency assignment by using monitoring data. And that's really innovative design, because we use here our interface to our spectrum management solution. We as LS Telcom are also a leader in spectrum management solutions, and here we have our solution MySpectra, and this will also be AI based. And we want to have an interface between both AIs, between the AIs of monitoring and of spectrum management. Why? Because of frequency assignment. And what we do here is that typically how it's done today, if spectrum management needs support from spectrum monitoring, an operator defines it, defines the campaign, defines the request, and this should be in future automated and done by the AI. So the AI should identify trends in license application. It should identify when monitoring support is needed, and then it should define which support is needed. It should define the campaign details, so which information is needed to give the spectrum management AI a good decision basis for the assignment process. So all the assignment process will be done by artificial intelligence, and the spectrum monitoring AI will only give to the AI of spectrum management a really condensed data set to base the decision on it. Here you can see again the interface. So we have MySpectra, our spectrum management solution, and our LS observer system, and everything is connected together. Based on AI, we have connected then all these two worlds together, so that the spectrum management can base their decision really on real-world data, and the AI will specify everything autonomously. yeah, this to the concept of AI-based frequency assignment. Now I'm already finished with my presentation, and if you have now any questions or comments to the things, maybe you have also heard about another trends in artificial intelligence or big data and spectrum monitoring, just let me know, just write into the chat, and I thank you now for your attention already. So I just read there are no questions so far, but if you have any questions, just write it to the chat. I will just stay in the session. So as I already said during my presentation, if anyone is interested in a specific and detailed presentation into different topics I mentioned today, please contact Alice Telcom, and we will provide you this presentation. Also for the Alice Observer, for example, we have a demo system here in Germany, and I can give you a live demonstration, for example, with the software. For the Spectrum Map, we have data which you saw from this reference project in Shanghai. Really interesting data, also with some interference or some illegal station we saw there. Can also give you a demo there, so just contact Alice Telcom. So now I think there are no questions, as I read it correctly. So thank you everyone again for your attention, and just let me know if anyone want to have a demo, just contact Alice Telcom. So thank you.